Hello everyone. In the previous class I have explained how to solve a linear differential equation with constant coefficients using the method of differential operator and method of variation of parameters of different types of function. In today's class I am explaining the next concept of the module, that is linear differential equation with variable coefficient. In that we have two types. One is Legendre's linear differential equation and Cauchy's linear differential equation. First start with the Legendre's linear differential equation. An equation of the form a naught into ax plus b whole square into y double dash plus a1 into ax plus b into y dash plus a2 into y is equal to phi of x. So this type of equation is called a standard Legendre's differential equation. Here ax plus b is the variable coefficient. Y double dash is the second derivative of y with respect to x. First derivative of y with respect to x and the dependent variable y, and phi of x is a function of the independent variable. Let us consider this as equation number 1. So this equation is called Legendre's linear differential equation of second order. To solve this equation, first we have to reduce this the equation, which is a linear differential equation with variable coefficient, to a differential equation with constant coefficient, and later we can solve that differential equation using the method which already discussed in the previous class. So first we have to reduce this one to the differential equation with constant coefficient. For that we have to go through the substitution. Let us substitute e power of t is equal to ax plus b. So replace that variable coefficient to a parameter. Let us take that parameter as t. E power of t is equal to ax plus t. By applying log for this function, take log on both the side, then we get log of e power of t is equal to log of ax plus b, where the value of log of e power of x is equal to x, since we get t here. Log of e power of t is equal to t is equal to log of ax plus b. Here we are replacing the variable x to the t variable. For that, ax plus b is equal to e power of t. Ax plus b is equal to e power of t. Ax plus b whole square is equal to e power of t whole square. And we have to replace this y dash in terms of t, because y dash is dy by dx, that is a derivative of y with respect to x variable, but we are replacing x variable in terms of t. For that we have to find y with respect to t. That means we have to find the value of dy by dx. To find dy by dx in terms of a new variable, I am taking this in terms of a composite function, that is I am inserting this new variable into this derivative, that is dy by dt into dt by dx. On simplifying this dt, we get the same term dy by dx, which is equal to dy divided by dt, where dt by dx is differentiation of t with respect to x. Here we have t is equal to log of ax plus b. Differentiating this one with respect to x, we get dt by dx. Differentiating with respect to x, we get dt by dx is equal to 1 divided by ax plus b. Differentiation of log is 1 divided by ax plus b into differentiation of ax plus b. Differentiation of x is 1 into a plus differentiation of this constant term is 0. So then remaining element is a divided by ax plus b. That is the value of dt by dx is a divided by ax plus b. Here in the equation number 1, we have ax plus b into y dash. Y dash is nothing but dy by dx. Dy by dx can be written as y dash On cross multiplying this denominator, that is ax plus b, we get ax plus b into y dash. So here we get this element ax plus b into y dash, which is equal to, what is the remaining term here? A is the constant term into dy divided by dt. Here we are replacing the variable x in terms of t. That is ax plus b y dash is equal to a into dy by dt. So this can be written as a into capital dy, where this capital D here, derivative with respect to t. Derivative of a variable, that is variable is y here, derivative of a variable with respect to t. So here we get the first term, that is ax plus b y dash, that is ax plus b y dash is equal to a into dy. So here we can replace this ax plus b into y dash to a into dy, that is this variable coefficient is reduced to a constant coefficient. In the place of ax plus b, we have just a element here. The variable reduced to constant term, that is the value of the first derivative element. Similarly, for the second derivative element, consider this obtained result. Consider that obtained result, that is ax plus b into y dash is equal to a into this capital D is d by dt, that is d by dt of y. To find the second order derivative, we have to differentiate this one more time with respect to x. On differentiating one more time, we get, here we have ax plus b into y dash. Here both the term containing x variable, ax plus b into y dash is dy by dx. That means we have to apply product rule here. Writing the first element as it is, product rule is first term, differentiation of the second term. Second term differentiation is y double dash, that is d square y by dx square, plus writing the first variable as it is, the second term as it is, that is y dash, into differentiation of the first term. Differentiation of x is 1 into a, plus differentiation of b is 0. So we left with a, that is ax plus b into y double dash plus y dash into a by applying product rule. In the RHS part, a is the constant term. Differentiating dy by dt with respect to x, we get a second order derivative of y with respect to x and with respect to t, d square y by dx dt. So the next step, ax plus b into y double dash plus a into y dash is equal to, here we have a into d square y by dx into dt. Keeping that constant a as it is, I am splitting this derivative as we have d square y by dx into dt. Splitting that as d by dx into dy by dt. So again, on simplifying this, we get d square y divided by dx into dt. And splitting this mixed partial derivative d square y divided by dx into dt as d by dx and dy by dt. Again, by writing this d by dx as a composite function, ax plus b y double dash plus a into y dash is equal to, writing the constant term as it is, writing this d by dx as a composite derivative, we get d by dt, writing this middle term as it is, dy by dt. Writing this derivative as it is, we have d by dx. This d by dx can be written as d by dt into dt by dx as a composite derivative. On simplifying this dt, again we get d by dx. Simplifying this, ax plus b y double dash plus a into y dash is equal to a into, here we have d by dt into dy by dt into dt by dx. But the value of dt by dx, here we have dt by dx is equal to a divided by ax plus b. dt by dx value is a divided by ax plus b. On simplifying this, cross multiply the value of ax plus b to the LHS. ax plus b into ax plus b, we get ax plus b whole square into y double dash plus a into, again cross multiplying for the second term, a into ax plus b into y dash. We left with a into a square, and this is a second order derivative of y with respect to t, that is d square y divided by dt square. d square y divided by dt square. So this can be written as ax plus b whole square into y double dash plus a into, in the previous simplification, that is in the first order derivative, ax plus b y dash is equal to a into dy. ax plus b y dash is equal to a into dy. So that means we can replace this ax plus b into y dash is equal to a into dy. So this can be written as a into dy. So this term can be written as a square into, here d square y by dt square, but the value of capital letter D is d by dt, hence this can be written as d square of y, second derivative of y with respect to t. Again simplifying this, we get, here we have ax plus b whole square y double dash. Again we need the same term in the equation number 1, ax plus b whole square into y double dash. We need this term, hence ax plus b whole square into y double dash, ax plus b whole square into y double dash is equal to, taking this term to the RHS, we get a square into d square y minus a into a square into dy, a square into d square y minus a square into dy. Again simplifying this, ax plus b whole square into y double dash, here the common element is a square is the common term, again d is also the common term. On taking d as a common element, we get remaining term as dy minus y. We can take y also the common term, the resultant term is d minus 1. a square into d into y is the common term, remaining element is d minus 1. So this is the value of second order derivative, the variable second order derivative with a variable coefficient to a constant coefficient. So this is the first order, ax plus b y dash is equal to, can be replaced by a into dy. ax plus b whole square into y double dash can be replaced by a square d into d minus 1 into y. In the similar way, if it is of third order, ax plus b whole cube y triple dash can be replaced by a cube d into d minus 1 into d minus 2 into y, and ax plus b whole to the power of 4 is into fourth derivative of y is equal to a to the power of 4 d into d minus 1 into d minus 2 d minus 3 of y. So these are the substitution to reduce a differential equation with variable coefficient to a differential equation with constant coefficient. So let us solve some problems on this type, that is problems on Legendre's linear differential equation. So the first problem on Legendre's linear differential equation is 1 plus x whole square d square y by dx square plus 1 plus x into dy by dx plus y is equal to sine of 2 into log of 1 plus x. to solve Legendre's linear differential equation, that is a differential equation with variable coefficient, first we have to reduce that equation to the equation with constant coefficient. For that we have to go through the substitution. So these are the procedures for that. In the first step we have to substitute e power of t is equal to ax plus b if ax plus b is the standard variable element. In the next step, on applying log, we get t is equal to log of ax plus b. If e power of t is equal to ax plus b, then t is equal to log of ax plus b. Then the value of the first derivative element, that is ax plus b into y dash, is equal to a into dy. Similarly, ax plus b whole square y double dash is equal to a square into d minus y, ax plus b whole cube y triple dash is equal to a cube into d minus 1 into d minus 2 into y. So these are the procedure. So in this problem we have 1 plus x in the place of ax plus b. That means the value of a is equal to 1, b is equal to 1. Here we have, in the given problem, ax plus b is equal to 1 plus x. That means a is equal to 1, b is equal to 1. So let us start with the substitution. Let us take e power of t is equal to 1 plus x. That is the first substitution. E power of t is equal to 1 plus x, then the value of t is equal to log of 1 plus x. Log of 1 plus x, and the value of a is equal to 1 and the value of b is equal to 1. Then the derivative values, that is ax plus b into y dash. Y dash is first derivative, ax plus b into y dash, where ax plus b value in this problem is 1 plus x into y dash. 1 plus x into y dash is equal to what we have, a into dy. Here the value of a is equal to 1, hence we get 1 into dy is the substitution for the first derivative element. Similarly, for the second derivative element, 1 plus x whole square y double dash is equal to 1 square d into d minus 1 into y. D into d minus 1 into y. So then the given equation becomes on substituting the substitutions, where capital letter D is equal to d by dt. Here we are replacing x variable in terms of t. After completing, we get solution in terms of t. In the final step we have to replace the variable, that is we have to replace t in terms of x. So now the given equation becomes 1 plus x whole square d square y by dx square is nothing but y double dash is equal to 1 into, that is 1 d into d minus 1 of y, plus first order element, that is 1 plus x y dash is equal to dy, plus here we have y is equal to sine of 2 times of log of 1 plus x. Log of 1 plus x is equal to t. So we get sine 2t. Simplifying this again, y is the common element. On multiplying this, d into d square, d into 1, d plus d plus 1 we have here, and the common element is y is equal to sine 2 times of t minus d plus t. So the resultant equation is d square plus 1 of y is equal to sine 2t is the equation which is a equation with constant coefficient. So the given equation is equation with variable coefficient. It is reduced to an equation with constant coefficient using the procedures. And here we have d square plus 1 of y is equal to sine 2t, and the solution of this equation consisting of two parts. One is complementary function, another one is particular integral. which I have already explained in the previous videos. To find particular integral, here we have sin 2t function, that means type 2 function. We have to apply the procedure of type 2. So to find the complementary function, let us start with the auxiliary equation. Auxiliary equation is m square plus 1 is equal to 0, m square is equal to minus 1, m is equal to plus or minus I. That is 0 plus or minus I is the obtained root, which is a complex root. Therefore, complementary solution. To write the complementary solution, here capital D represent d by dt. We are reduced that variable x in terms of t. In the given equation, we have the dependent variable y, independent variable x. Here we have to write the solution y in terms of x. But after taking the substitution, we are reducing the derivative d by dt. That is nothing but dy is equal to dy by dt. Here y is the dependent variable, t is the independent variable. That means we have to write the solution of y in terms of t here. So for the obtained complex root, yc is equal to e to the power of real term, that is 0 t into c1 cos, imaginary element is 1, cos 1t plus c2 into sin 1t. So this is the complementary function. Yc is equal to e power of 0t c1 cos t plus c2 sin t. Next, to find particular integral, that is to find yp. So formula to find particular integral is yp is equal to phi of, we are not writing x here, phi of t because it is a function of t here, phi of t divided by f of d here. F of d is differential operator equation, that is d square plus 1. So there we get phi of t value is sin 2t divided by f of d value is d square plus 1. Here the coefficient is 2, that means we have to replace d square by minus 2 square, d square by minus 2 square, which is equal to minus 4. So therefore we get yp is equal to sin 2t divided by minus 4 plus 1, which is equal to minus 3 sin 2t divided by minus 3. Therefore yp is equal to minus sin 2t divided by 3. So this is the particular integral. Therefore solution is y is equal to yc plus yp. Y is equal to, what is the value of yc? E power of 0t, which is equal to 1, remaining c1 cos t plus c2 into sin t minus particular integral, we have negative sign, minus sin 2t divided by 3, minus sin 2t divided by 3. So this is the solution in terms of t. But the given equation contains x as the independent variable. We have to write the solution in terms of x. But we are to reduce that variable coefficient to constant coefficient, we are taking that one more variable t in terms of x. After writing the solution in terms of t, we have to replace the t variable to x. Here the value of t is equal to log of 1 plus x. So therefore the final solution is y is equal to c1 cos of t value is log of 1 plus x plus c2 into sin of log of 1 plus x minus sin of 2 times of log of 1 plus x divided by 3. So this is the complete solution of the given Legendre's differential equation. To reduce the variable coefficient to constant coefficient, we have to insert a new variable After writing the solution in terms of new variable, in the final step we have to replace the original variable which is given in the problem, which is the dependent variable, that is x in this problem. Next problem is 3x plus 2 whole square y double dash plus 3 into 3x plus 2y dash minus 36y is equal to 8x square plus 4x plus 1. Here the value of a is equal to 3 and b is equal to 2. To reduce to this equation into a differential equation with constant coefficient, we have to go through the substitution, that is substitute e power of t is equal to 3x plus 2, then t is equal to log of 3x plus 2. According to this, the derivative values, that is 3x plus 2 into y dash, that is here the value of a is equal to 3, b is equal to 2, and the value of ax plus b into y double dash is equal to a into dy. Here the value of a is equal to 3, we get 3 into dy. Similarly for the second order, 3x plus 2 whole square y double dash is equal to 3 square, that is 9 into d minus 1 into y, where d is equal to derivative with respect to the variable t here. So now the given equation becomes what we have, 3x plus 2 whole square into y double dash. 3x plus 2 whole square y double dash is equal to 9 into d minus 1 of y, plus writing this 3 as it is, and 3x plus 2 into y dash, 3x plus 2 into y dash is equal to 3 into dy minus 36y is equal to 8 times of x value. So what is the value of x here? E power of t is equal to 3x plus 2. E power of t is equal to 3x plus 2. From this we have to extract the value of x. To get this x value, shift this to, that is x is equal to e power of t minus 2 divided by 3. From the substitution, x is equal to e power of t minus 2, on cross multiplying 3 we get e power of t minus 2 divided by 3. Then 8 into x square, e power of t minus 2 divided by 3 whole square plus 4 into e power of t minus 2 divided by 3 plus 1. So now simplifying this, on multiplying we get 9d into d, 9d square minus 9d. In all these three elements, y is the common term. So taking y as common term, remaining first element is 9d square minus 9d plus 3 into 3, 9d minus 36 of y is equal to, simplifying the RHS part, we get 8 numerator whole square divided by denominator whole square. Denominator whole square is 9. Numerator, that is in the form of a minus b whole square, that is a square e power of 2t plus b square, that is 4, minus 2 times of a into b, that is 2 into 2, 4 e power of t. 8 by 9 e power of 2t plus 4 minus 4 into e power of t. In the second term, 4 e power of t minus 2 divided by 3 plus 1. Simplifying again, plus 9d minus 9d get cancelled, 9d square, again we have 9d square minus 36 here of y is equal to 8. On taking 9 as LCM here, whole divided by 9, remaining element is 8 into e power of 2t plus 4 minus 4 into e power of t. That is the first element. Second element we have 3 in the denominator. On taking 9 here, we get plus 4 into 3 e power of t minus 2. Last term we have 1. On taking 9 as LCM, we get plus 9. Simplifying again, here in this term we have 9 as a common term. Taking 9 as a common term, remaining term is d square minus 4 of y is equal to 8 into, simplifying this, 8 into e power of 2t plus 8 into 4, 32 minus 32 into e power of t. Second term, 4 into 3, 12. 12 into e power of t minus 12 into 2, that is minus 24 plus 9 whole divided by 9 here. On cross multiplying this 9, we get 9 into 9, 81. So that is common for all the numerator terms. Hence d square minus 4 of y is equal to 1 divided by 81. 9 into 9, 81. So remaining element e power of 2t, this is the only term which containing 2 as a power, 8 into e power of 2t, and the terms containing e power of t is minus 32 plus 12. Minus 32 plus 12 is minus 20 e power of t. Remaining constant term 32 plus 9 minus 24. 32 minus 24 is 8 plus 9. 8 plus 9 is 17. So the obtained element is d square minus 4 of y is equal to 1 by 81. 8 into e power of 2t minus 20 e power of t. 32 minus 24 plus 9. The remaining constant term is 17. So this is the obtained differential equation with constant coefficient. To find the solution of this, we have to find complementary function using the LHS part of the equation and particular integral from the obtained the function e power of 2t, e power of t and a constant term. Here we have exponential term, that is we have to find particular integral using type 1 procedure. So now let us find complementary function. So to find complementary function, auxiliary equation is m square minus 4 is equal to 0. Then m square is equal to plus 4, m is equal to root 4, which is equal to plus or minus 2. Plus or minus 2 is the real and distinct root. Therefore, complementary function, that is yc is equal to c1 e to the power of 2t. We have to write the solution in terms of t here because capital D represent d by dt plus c2 e to the power of minus 2t, that is the value of yc. Next, to find particular integral, to find yp, we have yp is equal to, so writing the numerator, the RHS term into 1 by 18, that is 1 by, the formula is phi of t divided by f of d, where the phi of t value is 1 by 81 is common, into 8 e power of 2t minus 20 e power of t plus 17 whole divided by f of d value is d square minus 4. Here we have 3 elements in the numerator. We have to find a particular integral for each element. Therefore, yp is equal to 1 over 81 is common for all the terms. 8 e power of 2t divided by d square minus 4 minus 20 e power of t divided by d square minus 4 plus 17 divided by d square minus 4. Here we have e to the power of 2t. To find a particular integral for this, we have to replace d by 2. Since we have 2 here as a coefficient, in the second term we have to replace d by 1, e power of 1t. And in the last term we have a constant term. For the constant term we have to take e power of 0t, because e power of 0t is equal to 1. Hence here we have to replace that d by 0, because 0 is the coefficient. Next, on simplifying, yp is equal to 1 over 81 8 into e power of 2t divided by 2 square, that is 4 minus 4 minus 20 e power of t divided by 1 minus 4 plus 17 e power of 0 is 1, 0 minus 4. Here in the first term we have denominator term as 0. That means we have to continue further procedure for the first term only. In the second term we get minus 3, here we get minus 4. Then yp is equal to 1 by 81. If we get denominator as a 0 term, then we have to multiply the independent variable to the numerator, that is t into e power of 2t divided by, we have to differentiate the denominator. Differentiation of d square is 2d. Differentiation of d square is 2d minus 20 e power of t divided by 1 minus 4 is equal to minus 3, minus of minus plus 3, 0 minus 4 is minus 17 divided by 4. Here we have 8t e power of 2t divided by 2d. So therefore we have to replace d by 2 again in the first term. So then particular integral value is equal to 1 over 81 into, on replacing d by 2 we get 2, 2 into 2 is equal to 4. So hence 8t e power of 2t divided by 4 plus 20 e power of t divided by 3 minus 17 divided by 4. Again simplifying this, 4 1s are 4 2s are. So final particular integral value is 1 over 81 2t e power of 2t plus 20 e power of t by 3 minus 17 divided by 4. So now we have to write the complete solution, that is complementary function plus particular integral. That is complete solution is y is equal to yc plus yp, which is equal to yc value. What is obtained yc value? c1 e power of 2t plus c2 e power of minus 2t plus obtained particular integral value is 1 over 81 2t e power of 2t plus 20 e power of t divided by 3 minus 17 divided by 4. So that is the solution in terms of t. But we have to write the solution in terms of x here, because x is the given independent variable. That means we have to replace the t variable in terms of x. That is the value of t is equal to log of 3x plus 2. The value of t is equal to log of 3x plus 2 and the value of e power of t is equal to 3x plus 2. So in the place of 3x plus 2, that is if e power of 2t is there, we can write this as e power of t whole square, because we have the element e power of t only. So that's why writing this as y is equal to c1 e power of t whole square, c2 e power of t whole to the power of minus 2. So to the power of minus 2 we have. Next term 1 over 81 2t e power of t whole square plus 20 into e power of t by 3 minus 17 by 4. So the remaining part is we have to replace the variable t in terms of x. On replacing t in terms of x, we get the final solution, that is y is equal to what we have in the first term, c1 e power of t. E power of t is equal to 3x plus 2 whole square plus c2 3x plus 2 minus to the power of minus 2. Next term plus 1 over 81 into 2 times of t. T value is log of 3x plus 2 into 3x plus 2 whole square plus 20 into 3x plus 2 divided by 3 minus 17 divided by 4. So this is the complete solution of the given Legendre's differential equation. Here in this term we can write this as 3x plus 2 minus whole square, 3x plus 2 to the power of minus 2 we have. This can also be written as 1 by 3x plus 2, that is as, or we can write the solution as C1 3x plus 2 whole square plus C2, since we have minus 2 in the power, 3x plus 2 whole square in the denominator plus 1 over 81, 2 times of log of 3x plus 2 into 3x plus 2 whole square plus 20 times of 3x plus 2 divided by 3 minus 17 divided by 4. So this is the solution of given Legendre's differential equation. Next problem on Legendre's linear differential equation is 2x plus 1 whole square y double dash minus 6 into 2x plus 1 y dash plus 16y is equal to 8 times of 2x plus 1 whole square. So in this problem the value of a is equal to 2, b is equal to 1. The general form is ax plus b. Here a is equal to 2 and b is equal to 1. Let us take the substitution. Let us take t is equal to log of 2x plus 1 or e power of t is equal to 2x plus 1. T is equal to log of 2x plus 1, e power of t is equal to 2x plus 1, where the value of a is equal to 2 and the value of b is equal to 1. Also we need x value, that is x is equal to e power of t, shifting this plus 1 we get minus 1 divided by 2, and the derivative substitutions are ax plus b into y dash is equal to a into dy, that is 2x plus 1 into y dash is equal to 2 times of dy. Similarly for the second order, 2x plus 1 whole square y double dash is equal to 2 square, that is 4 into d minus 1 of y, where this capital D refers as d by dt, that is a derivative with respect to t, derivative of a variable with respect to t. So then the given equation becomes, on substituting these values in the given equation, it becomes, first term we have 2x plus 1 whole square y double dash which is equal to 4 times of d into d minus 1 of y. First element is 4d d minus 1 of y minus 6 times of 2x plus 1 into y dash which is equal to 2 times of dy, which is equal to 2 times of dy, and the last term plus 16y is equal to 8 times of 2x plus 1 whole square. 2x plus 1 is equal to e power of t whole to the power of 2. Simplifying this again, we get 4d. Y is the common term in all the three elements. Remaining term is 4d square minus 4d square minus 4d minus 12d plus 16 of y is equal to 8 times of e to the power of 2 into t. 8 times of e power of 2t. So here this is a function of type 1, that is a exponential function. Simplifying this again, 4d square minus 4d minus 12d is minus 16d plus 16 of y equal to 8 times of e power of 2t. Simplifying again, here we have 4 as a common term, then d square minus 4d plus 4 of y is equal to 8 times of e to the power of 2t. Simplifying this again, 4 1s are 4 2s are, the obtained result is d square minus 4d plus 4 of y is equal to 2 times of e power of 2t. So this is the obtained equation with a constant coefficient. So this is a differential equation with constant coefficient. We reduce a differential equation with a variable coefficient to a constant coefficient. So now let us find the solution of this equation, that is yc plus yp. So to write the value of yc, first we have to take auxiliary equation, that is m square minus 4m plus 4 equal to 0. So on solving this equation, this is in the form of a square plus b square minus 2ab, where the value of b is equal to 2. A square plus b square minus 2ab. So hence we get m minus 2 whole square is equal to 0. This is in the form of a square plus b square minus 2ab. A minus b whole square is equal to 0, where b is equal to 2 here. So this can be written as m minus 2 equal to 0, m minus 2 equal to 0. Therefore m is equal to 2 comma 2 are the obtained roots. That is, we get real and coincident roots. Here both the roots are same, 2 comma 2. Therefore for this complementary solution is yc is equal to, we have to write y in terms of t here, because capital letter D is d by dt. So on writing yc for real and coincident root using case 2 solution, that is c1 plus c2t into e to the power of 2t. This is the complementary solution. Here in the final step we have to replace t by log of 2x plus 1. Next, to find particular integral, that is yp value. So to find particular integral, that is yp, formula is yp is equal to phi of t divided by f of d. What is phi of t here? Phi of t is equal to 2 times of e power of 2t. Phi of t is 2 times of e power of 2t, and f of d value is d square minus 4d plus 4, or simply we can take in the first step I write as it is d square minus 4d plus 4, or we can write that as d minus 2 whole square. Here in the next step we have to replace d by 2, because the coefficient of the variable is 2 here. To get particular integral we have to replace d by 2. Replace d by 2 here. On replacing d by 2 we get yp is equal to 2 e power of 2t divided by 2 square 4 minus 4 into 2 8 plus 4. On simplifying the denominator, 4 plus 4 8 minus 8, the denominator get cancelled. Here the value of denominator is equal to 0. If denominator equal to 0, we have to continue till we get a non-zero denominator as a particular integral. For that, in the next step we have to multiply the variable, that the independent variable, to the numerator, that is t into e power of 2t, and then we have to differentiate the denominator. Differentiation of the denominator is, differentiation of d square is 2d minus differentiation of 4d is 4 plus differentiation of a constant term is 0. So hence we get 2d minus 4. Again replace d by 2. Again replace d by 2 here. On replacing d by 2, here we get 2 times of t into e power of 2t, 2 times of t into e power of 2t divided by 2 into 2, that is 4 minus 4. Again 4 minus 4 get cancelled, we get 0 remainder. That means we have to continue further. Next step, yp is equal to multiply one more t to the numerator, again differentiate the denominator. Multiplying t again, 2 t square we get e power of 2t. On differentiating the denominator, 2d derivative is 2 differentiation of minus 4 is 0. So we get 2 times of t square e power of 2t by 2. Here we left with a non-zero denominator and d term eliminates here after differentiating. So no need to substitute the value of d because d value not here. So we left with a constant term 2 and that constant term get cancelled 2 by 2. The resultant term t square e to the power of 2t. So the particular integral value is t square e power of 2t and complementary solution is c1 plus c2t into e power of 2t. So therefore the solution is y is equal to yc plus yp where the value of yc is equal to c1 plus c2 into t into e power of 2t and the value of particular integral is t square e power of 2t plus t square e power of 2t. So this is the solution in terms of t. But in the given problem the independent variable is x, that is dy by dx. We have to write the solution in terms of x here, hence replacing the t variable to x variable. The value of t is equal to log of 2x plus 1. Log of 2x plus 1, here we get y is equal to c1 plus c2 into t value is log of 2x plus 1 into e to the power of 2t. E power of 2t can be written as e power of t whole to the power of 2 where the value of e power of t is 2x plus 1. So hence we get 2x plus 1 whole square, that is the complementary function, plus what we have for the particular integral t square e power of 2t. Again the value of t is log of 2x plus 1, log of 2x plus 1 whole to the power of 2 t square into e power of 2t. Again e power of 2t value is 2x plus 1 whole square. So this is the value log of 2x plus 1 whole square into 2x plus 1 whole square. This is the value of complementary function and particular integral in terms of the given independent variable x.